Hi everybody, I'm Errichto, and this video will have two parts. The first one is summary of week 1 of 30-day LeetCode challenge. How was it for me to participate daily, what I think about problems, and am I tired of making videos, so many videos. Second part is harder versions of those problems. I will talk more about Divide and Conquer for max subarray and also the quadratic version of DP for buy and sell, if I remember correctly, and even IOI 2015 problem horses, so even harder version as suggested from the comments. First, some overview of problems. Also, timestamps are in the description. Some overview of problems. After first 3 days, I complained a lot. Single number, happy number, and maximum subarray. People misunderstood me as if I'm complaining about too easy problems. No, it's not that. I already said in the past, those are too much about knowing this exact thing. Like very ad hoc, not really about thinking. Move zeros was the first nice problem. Best time to buy and sell, I don't have an opinion. Group anagrams, I don't know. And counting elements is a fine programming exercise, but isn't really about algorithms. It's just about knowing the technique of, well, hash set. This is the last video, not published yet at the moment of me recording this summary video, but it should be already public now that you are watching the video. Judging from first week, I would say just every next week will be a jump of difficulty, because here the difficulty didn't increase. All 7 problems were similar, maybe move zeros and maximum array, happy number, those 3 maybe were hardest actually, maybe group anagrams as well, but it isn't true that counting elements is harder than first 2. At least in my opinion. So I expect week 2 to just be now medium problems, maybe easy medium, medium hard, and hard, I would say. Well, just those 2 problems can be very hard, like hardest LeetCode problems maybe. And I recorded a video a day, and most of the time it was very fine, but when it collided also with Google Code Jam qualification round, then I had a lot of work to do. So I wouldn't want to do 2 or 3 videos a day, because that's recording. Well, first thinking about recording in terms of Code Jam, I need to prepare some slides, stuff like that. Then also editing and, I don't know, answering comments, uploading to YouTube. It also takes time, so that's too much. But video a day is fine, though after April I will take a few days break from making videos. What else about this? Does LeetCode choose problems correctly? It isn't that bad now. For first 3 days it was bad, now I'm quite happy. I'm just hoping to see a bigger challenge in the future. And as promised, I will move to talking about harder versions of something. For day 3, maximum subarray, I will talk about divide and conquer approach, which was mentioned. It was mentioned in hints or follow-up. If you have to figure out linear solution, try coding another solution using divide and conquer approach, which is more subtle, and I will give you one more problem for divide and conquer. Then here I will talk more about what I already mentioned in initial video, DP of NN. What if we were allowed more than 1 unit of stock in our hand, and square solution, but also I will talk about n log n with a segment tree. And from this we will move to IOI problem horses. Timestamps in the description. Enjoy. Given a sequence, let's find a maximum subarray with maximum sum, using divide and conquer. Brute force is of course to try every interval and to check from I to j, for every pair ij, to sum up the elements and consider that to be the answer, but we'll use divide and conquer. And this boils down to the following. Split in the sequence in the middle, find the best interval, the best subarray that passes through the middle. So I don't want to now consider intervals like that. Everything that is like that can have just one element on the left and maybe everything on the right. It's all fine. Brute force would again be to iterate over every possible start here, every possible end over there, and to find the sum in the process, but we want something faster. The goal complexity, by the way, is n times log n. Slower than Cadence algorithm, but it's just a possibility, a way to learn a method, divide and conquer, to solve harder problems later. How to find the best interval that passes from middle? How it helps us that it's middle, even if we don't know the P or cadence algorithm. Well, if I will say that this is for sure not the best interval, because here we have sum -8 and we can do something better on the left. Actually, when moving from the middle to the left, I can compute cumulative sum. It will be -3, -8, -3, -5, -2, and so on. And I will choose the best of them. Actually, it turns out I think this is the best. The sum of those elements is -2, and this is the best we can achieve when going through the middle to the left. I will independently, let's say with another color, do the same to the right. Move from the middle to the right, computing cumulative sum. 1 plus 2 is 3, 4, 2, 3, 4. Then either this prefix or this one, doesn't matter, let's say this one, they will be best possible. And now I say we combine that. I'm considering this whole interval. With value -2 plus 4, the sum is 2. This is best interval, the maximum possible sum of interval that passes through a middle of a sequence. But you might say, well, this is not the answer, we can get something better. In particular here, 3 minus 2 plus 5, this is what, 6. It's better. But after computing this, we recursively go into each half. We split it in the middle, we found the best interval like that, and now recursively run for this sequence and solve that sub-problem. Also recursively run for this sequence. So solution that is run, function that is run for sequence of length n, it runs 2 instances of size n over 2, n over 2. Then that runs instances of size n over 4, n over 4, and so on. Each of them separately, like this one, of size n, is done in O of n, before recursion, when we just move from the middle to the left and to the right. In total, O of size of this interval that we deal with. When we are left with half of elements, the complexity of finding the best interval passing through the middle is O of, again, size, O of n over 2. This runs also n over 4 and so on. And this all sums up, just like in, for example, a segment tree, to n log n. A proof for that would be to check to see the total running time of every level of recursion. In each of log levels, the sum is n. I don't want to go into detail, but this is why the total complexity is n log n. So even if the optimal interval doesn't pass through the middle, we later recursively go through that half. We here cut in half again. We will find the best part to the right, best part to the left. We will combine that and we will get 6. I will show you implementation of this. And I will even submit this to LeetCode. I have a lot of code over there. Let's remove all of that. I think it was for the sake of some other problem. Max subarray of nums. Let it run itself recursively. Is that okay? I guess so. Max subarray. I need size of an array. If this size is just 1, then return the only element. The problem asks for the best non-empty interval. Even it's negative, we need to return that. Now we have indices from 0 to n minus 1. Let's say that middle is n over 2. It will be last element if in left half. I can increase this a little bit. Last element in left half. So we have from 0 to middle, and from middle plus 1 to n minus 1. Best left is, I will correct that in a moment. For everything from mid to 0, there is some cumulative sum. Sum plus equal nums of I. Best left is minimum of itself and sum. Sum is initially, no, best left is initially some minus infinity. Right now plus infinity because we minimize. again, this problem is a bit harder because of negative values. We do the same for to the right part. Starting from mid plus 1 to the end. Sorry for not being consistent with plus plus before and after a variable. Best right is minimum of itself. Actually maximum. Oh, this is why I wanted to put minus infinity. Int min. All the codes I will put in the description. I should have said that at the beginning of the video. Now all the codes for 7 problems are in my GitHub repository. We maximize, and what will be returned is best left plus best right. This would be true if I was just interested in intervals passing through the middle. Right. But this is not true, and we need to run recursively as well. Let's say left. There is a way to do that in C++ smartly. I think nums begin to nums begin plus mid plus 1. This is iterator for element after that one. Nums begin plus mid plus 1 up to nums end. This is how you get subarray in C++. And I say answer is best left is maximum of solve. How is the function called? Max subarray. Max subarray of L, max subarray of R, and also best left plus best right. To get maximum of 3 values, you need to put brackets like those. Return answer. I didn't need a variable answer. I could just return that directly. Compilation error, max of single thing, sum. Compilation error again, missing semicolon. Pending, judging, and random error. Let's try to find it together. Likely it means an infinite loop. Or can I get an empty thing? I don't know. It means an infinite recursion, or I try to access something outside of the array, but maybe infinite recursion. Is this correct for sure? Middle. For n equal to 2, that is not correct. This should be first right, because for n equal to 2, I will compute mid as 1, and I will think that left interval is from 0 to 1. That's not correct. I should round this down. Now for 2 it will be 0, for n equal to 3 it will be 1. That's fine. I should have thought about rounding before and what exactly happens for n equal to 2, because it's kind of a special case. I could also make an if. If n is 2, then return maximum of first element, second, and first plus second. Not to worry about that. Done. And complexity of this is n log n. As promised, I will tell you one more problem that you can solve yourself with this. There's a thing called monotonic queue, and it can solve the following problem. Given a sequence and an integer k, for every interval of size k, for every subarray of length k, find its maximum. And this is usually solved with monotonic queue. But there is an alternative solution. This is, let's say, normal solution. Alternative is divide and conquer. And if you don't know monotonic queue, then this is really easier, because we split in the middle, and then we want to solve all those things that pass through the middle. And for that, a bit similarly to this, we go from middle to the left and from middle to the right, and we compute prefix and suffix maximum, and we combine that to find all the answers for intervals that pass through the middle. Then we run recursively into 2 halves to find answers for those smaller intervals over there. Next problem to talk about is day 5, best time to buy and sell stock number 2. And a lot of people in the comments pointed out that something easier works. Instead of my DP, I will get rid of this. Instead of my DP, we iterate with I up to prices size -1, answer plus equal, max of 0, prices of next element minus prices of I, return answer. And that's it. Also O of 1 space and O of n time complexity. I will explain to you why it's correct. Also, alternative way to write this is if next price on the next day is greater than my price, then add the difference to the answer. And it helps to draw this graph of prices. Maybe, for example, let's use this 715364. We can visualize the graph of prices. On day 1, the price was very big, 7, then it was very small, 1. Of course, it will not be 100% accurate, this graph. 1, 5, 3, 6, and 4. What is optimal here? Maybe we can, I will say that green is buy. For sure, I should buy over there. And sell here, buy, and then sell over there. So that isn't actually, it is pairs of consecutive days. But what would happen if I changed those two, 4 and 6? Then let's redraw that. The graph would look like this. And I would say it's optimal in this problem to this time buy here for 3 and sell here for 6 to get a difference of 3, to get the profit of 3. But how does it work? Why is it correct to just take differences like this? Well, because when function increases, we can imagine this as a big function. When function has a long increasing part, even could consist of a lot of values, and for such a thing it is optimal to buy low and sell high. Instead, we can say that for every such segment to the answer I add this distance. And it doesn't necessarily mean we buy here and sell here, though we could say that. But then after a moment buying here and selling there, it cancels this place because we buy and sell. So as well we could say this place doesn't exist, and so on. So the optimal answer of this distance, sorry for being for covering the drawing, this distance, it is equal to the sum of all those smaller distances. Just think here what happens if you draw a graph of prices, what is optimal. That was first easy part, and now I will talk again about dp of nn. What happens in this problem if we can hold more than 1 unit of stock? I already explained that a bit over there, but today I have code, stocks, I will go through it. dp of I units, let's define dp of I units as maximum possible amount of money we have after first I days with that many units in hand. Because it doesn't matter when exactly we did what in the past, just important how many units we still have. And transitions are exactly as I described them here. From day I, we can move to I plus 1 by having the same number of units, and that's this line. We can do nothing. From dp of I units move to dp of I plus 1 units. Function max self for me is just this. A is max of A and B. It's like a shortcut. Just like plus equal, it will do A is equal A plus B. Then max self is that plus equal for maximum. And if to get today I could get with 15 money, then I can have 15 money on day I plus 1 with the same number of units in hand. Also, from dp of I units, we can move to the number of units smaller by 1, and then we increase our money by the price of I, but because this means sell. Similarly, buy, we can increase our count of units by 1 by paying the price. And at the end, on day n, you want to have 0 units. That's your answer. Complexity is n squared. But something harder, also n squared, but can be improved to n log n, will be here, this greedy-ish solve. And if you add segment tree on the top of that, it becomes n log n. I will not go into segment tree, because half of you will know it, and for them it will be too easy. Half of you doesn't know segment tree, then this short video isn't enough to explain all of that. And this is not a good problem to learn that right now. First, a drawing for what's the idea behind this solution. If you have a sequence of days, a sequence of prices, then we can, let's say, buy over there, buy, we can maybe sell, buy, sell, 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 buy, and now something is wrong. This is impossible to achieve. Well, first of all, the number of buys is too small. Now, there are 5 buys and 5 sells. But after this moment, we have 2 units, 1, 2, 1, 0, minus 1. At this moment, we cannot sell, because after this prefix, the number of buys and sells are equal, so we don't have units. This sell is impossible. So the sequence of sells and buys and doing nothing, like here it's do nothing, it's valid if for every prefix we have the number of cells is at least equal to the number of buys. It's a bit similar to bracket sequences. Like the sequence of brackets is valid if the number of opening brackets is not smaller than the number of ending brackets for every prefix. And at the end, the number of buys and sells must be equal. This is related, at least, in some way. But it's not that useful of an observation, but it's an example of what happens with harder problems. We need to find similarities with other problems in order to know what we are looking for and what we should try. But for those, just like with bracket sequence, maybe it is useful after all. Let's treat every buy as +1 to our number of units, and every sell as -1. Every nothing is 0, and the task is this. Create a sequence of 0, 1, and -1 so that the sum of everything would be 0, and every prefix would have non-negative sum. And this turns out that we can do greedily if we sort numbers and look from the greatest one. Let's say that initially this is the sequence, we know nothing, and there is some day with biggest price. Maybe here the price is 1000. Then it would be awesome to sell, so to put -1. Is it possible to put -1 here? Of course, because we can buy on any of previous days. So this solution is partially greedily because first we assume that everywhere we buy, so we have a lot of units, not infinite number of units, but what if we buy everywhere? Then going from highest prices, we try to say, okay, here I sell. And we change +1 into -1. What about here maybe second last price, second highest price, 990. Can I put -1 over there? I cannot, because prefix becomes negative. And this makes sense. On the first day I cannot sell. But I don't want to buy for such a high price. So because I cannot reach -1, this is impossible, maybe I can just get 0 over there. Is it okay to do nothing on this day? Yes, it is. No prefix became negative, so I'm putting here a 0. Then I'm looking at third smallest value, third highest price, maybe here it's 950, and I'm trying to change this to -1, which means I will sell for this value. Indeed, right here I can put -1, no prefix became negative. This is exactly the logic that I implement. It's intuitive that it should work because I prioritize selling for high price. If possible, I sell for the highest price. If not possible, I at least do nothing there. And for now, I for a moment assume that everything with smaller prices, I buy there. Because it's okay to buy for smaller price to now sell for my higher price. And now I will walk you through the code. I didn't give you a full formal proof of a correctness, but I'm just saying it's kind of intuitive, and that's it. Otherwise, we would need now an entire lecture for formal proofs and greedy solutions. And by the way, DP and greedy are often hard to distinguish. When you see a problem about sequences and doing something with them, often it's guessing whether greedy works or not, and if not, then use DP. So what's this greedy solve? Iterate over days. For every day I, insert pair, price, and I in a vector of pairs. Sort them decreasingly. Now, from highest price, I will do something. Decision is a sequence of initially just plus ones. In C++, it's okay to put a plus. It doesn't do anything. It's equivalent to this. I prefer to write +1. So initially +1 means to buy everything. Then first for highest price, I will say, oh, maybe I can sell over there. I will get back to this function in a moment. And in this sorted order from highest, the second element of a pair is position. Where is position? I try to change the decision on that day from +1 to -1. I try to sell. And if is okay, then continue. So then it's okay, we leave -1. Is okay is function to check if any prefix became negative. Prefix is initially 0, go through the whole sequence from left to right, add x, -1, +1, or 0. If not, if it's negative, then return false. This is not okay, because it's not allowed. If it never goes below 0, then return true, it's okay. So right now I'm not requiring the sum to be 0, because I'm starting with +1, +1, +1, so the sum is big. But I will keep changing from +1 to 0 or -1. Eventually the sum will reach 0. Actually. If changing to -1 was okay, then I can say continue, and I move to the next highest day. If possible, for this high price, because in the future I will consider only smaller prices. If possible, I want to do nothing right now. I don't want to sell. It will, okay, this should be buy. I don't want to buy for this price. It's better to buy for lower prices, if possible. So change this to 0, and I check if that's possible. If not, then apparently we must put +1 here. Greedily, starting from highest price, if possible, I'll sell over there and check if it's possible at all, even if I need to buy everything else. I don't want to prove that at the end everything becomes 0, but well, the sum of values, it will slowly decrease. That's some intuition behind it. At the end, money is 0. I iterate through all the decisions, and every +1 means to buy. So my money decreases by the price at day I. If -1 means to sell, my money increases, return money. And this code, which by the way is available on GitHub, link in the description. I have function for DP solve, greedy solve. And in main you can see that in infinite loop, for repeat starting from 1 going forever, I generate random n from 1 to 15. This is a function to generate random thing from A to B. Get random n, length of a sequence from 1 to 15. Prices, choose each one between 1 and 15. I didn't want too small values or too big, because this is the best. If there is some counterexample, it will find it in time. And then print that test, run dp solve and greedy solve, and assert that those two values are equal to answers. When I now run this, you will see something like that. Right now I'm at repeat equal to 5000, because here I'm first printing the iteration, which iteration of a for loop it is. And I stopped it for a moment. In repetition number 11,000, this was the sequence 1, 8, 12, 14, and both solutions said the answer is 17. Because here we should do what? Buy at price 1 and buy at price 8. I spent 9 money. I will sell at those 26. The difference is 26 minus 9, 17. And it continues. So after this, I can be sure that even though I'm not submitting this code, it is correct. I wanted to do this obviously before explaining the solution and implementation to you, not just blankly assuming, yeah, I think it's correct. It's good to either have a formal proof or stress testing, so to test on multiple tests, or to just submit to an online judge, and then you know it's correct, assuming that tests are strong enough. Now that we're done with this, we can move to the to how to use a segment tree here, because right now it's quadratic. There are n positions. For each of them, I check if I do something. I check if prefix became negative. Function is check is linear of n, and I run it linear number of times. Total is n squared. And it turns out that isOK can be replaced with a segment tree, a check on segment tree. If you have a problem, like there is a sequence, handle queries that are change value and check if some prefix is negative. By the way, it's equivalent to this. Change prefix, for every element in prefix add something, and check if anything is negative. I don't want to go into that. This can be done with segment tree, or this can be done with segment tree, it's equivalent. If you know segment trees, you should be able to do it. And then you change one element in the segment tree, you run a query about minimum, you check if it is smaller than 0. If yes, you roll this back, so you change it again. And each such query will be log of n. So isOK will move from O of n to O of log n. And thus the whole complexity becomes n times log n, faster than dp. If you didn't understand something there, then I have two things to say. First, you can ask me questions in comments and I will reply, but you need to ask about something specific. A comment, I don't understand it, I cannot help with that. I will not re-record a video and say exactly the same. Why would it help? You can ask about specific moment and provide a timestamp and ask some question. Or the alternative is just that maybe it's too hard for you. If you don't know segment trees, then don't try to understand this solution. Of course, like how to improve from O of n to O of log n, because it requires some technique. One final thing about this is that I won't be surprised if it can be done without a segment tree and with some priority queue or set instead when going from left to right, but I didn't try to solve it that way. So if somebody knows that it's correct, you can implement something similar, take my code, write a new function, stress test against that, and then describe in the comments. The last point for today is to talk about IOI 2015 problem horses. And somebody in comments said that it's like this problem from a moment ago, but on steroids. Here we have n years, just like n days. On each day there is some price of a horse. Price is y of I. But also there is growth coefficient x of I. You start, I believe, with a single horse. I don't remember. Do you start with a single horse? Let's assume so. It doesn't matter. Let's say you start with a single horse. On every year you can decide how many horses you sell, maybe all of them. But whatever is left, there is some growth coefficient. If it's equal to 3 and you had 10 horses, then next year you have 30 horses. So maybe it's good to save your horses so they would multiply. But maybe it's better to use the fact that price is very good today or this year and sell some part of horses, some part of your herd. In this problem also we have queries about, we have updates, the price and the growth coefficient, they can change, and that can be done with a segment tree. So again, I will not talk much about it, but what would happen if we are just given that input? And the answer should be printed modulo billion plus 7. Again, if you never saw something like that, then don't worry about it. I will not, but also I will not explain, just assume there are no issues with huge integers. Let's say that price on the first day is 10, then there is growth of times 3, then the price is 18, or maybe not 8, growth is 2, and price is 3. And you start with a single horse. You can sell it on the first day and get money equal to 10 for that, and you're done. Or you can wait one day, then from one horse you will get 3 horses, and on second day they are worth 24. Or you can wait one more day, you will get 6 horses, per price of 3, you will get 14, 18 money. It turns out that here the best is here, or maybe it's better to mix. Observation number 1, it's optimal to sell on one day, not to mix. Because when you look at any 2 days, they can be consecutive or not. But you can think this. If I had a single horse on that day, and I let it grow, and so on, and it will turn into some number of horses into that later day, here it would be just 2 horses, then I can see how much money I would get from this. Here, 6 money. So with 1 horse on this day, I can either sell it now for 8, or wait, let it multiply, and it will have a value of 6. It's better to do it now. But always it's about comparing price of I versus price of some j in the future times the products times growth between I and j. And this is a proof why it isn't optimal to do something on 2 days. Just choose a day that will give you best kind of ratio. If you think, oh, maybe sell some horses today and sell some on some other day, just compare those 2 values. If they are equal, then do whatever, let's say everything on the first day. Otherwise, choose the bigger value. Now that we're done with this, it turns out that we just need to, for every day, to compute what kind of score we would have from this. And on day I, we can get answer P of I times growth of 1 times growth of 2 times and so on times growth of I, or like I minus 1, growth before day I. And seems reasonable to go from left to right and just compute those products. But now, okay, now there's some issue with big integers. If values are like 1 billion, then this quickly overflows integer or long, int or long. Even in Python, where you can't have big nums, the complexity of doing anything with those numbers becomes big. Operation, single multiplication of 2 numbers is O of 1, assuming that they are short. This product, it will have around n digits of this magnitude of digits. And then every multiplication is O of n. So the whole complexity becomes O of n squared instead of O of n. And to do it faster, we can have some observations. And here it's the following. If when comparing I and j over there, when we see this growth in the middle, if I and j are far away from each other, then this growth is huge. Even if every day just the growth is times 2, then after 30 days it becomes 2 to 30, more than 1 billion. No matter what prices are there in the input, between 1 and billion, this will be better. And this means that for a long sequence of million elements, like n elements, only the last 30 makes sense. You need to only compare that, because you know that the last one is so much bigger because of growth than this one and anything before that. This length is 30 because 10 to 30 is bigger than whatever price there is here, let's say pi, because prices in the input, in the statement it was set prices are up to billion, well, this is greater than billion. All of that isn't really true if, so what if growth is 1? What if growth is equal to 1? Then it isn't true anymore, and because of that you need to use some segment tree and, or maybe not, set or hash set or whatever, set of positions where growth is not equal to 1. There are some positions where growth is 2 or greater. And now the trick is this. You go for this set from biggest positions. This is set of pairs, let's say, set of just indices. So set of indices, go from biggest elements, and you only need to consider 30 of them. Or you can keep like some product starting from 1 and multiply by values. If this growth is 3, this one is 5, then you already have product of 15, and once this product reaches 1 billion, you can stop. And when you have something, everywhere in the middle, the growth is 1, so it doesn't change. So in the middle, you need just the biggest price. The complexity after some pre-processing, after finding those positions and updating set, it will be O of 30 times, because this is how many things we will check, times asking for the biggest price here in the middle, in those intervals of segments. And now this can be done with a segment tree. We will keep asking about, hence the complexity will become log of n, 30 times log of n. We will ask segment tree, what's the biggest price here? So I will consider that to be, oh, it's over there. So I consider that maybe this is the answer. Then I consider to sell over there, but also ask a segment tree for maximum over here, and so on. Just, you cannot ask about product of all those values. Just ask compared from the end. So use this product, this relative product. You don't want to find the absolute answer. You want to just compare things. And only going through last 30 elements. If you want really details on this, then there is PDF editorial. I will put a link for that somewhere below. And you can do it. But of course, if you are just average LeetCode user, then you shouldn't worry about problems like this one. It's just something related, recommended by a comment, so I wanted to at least mention it. And this will be final complexity, by the way, per a query, per an update, because there are updates that will change the input. Oof, that's everything. I hope you enjoyed the video. If yes, leave a like, subscribe to the channel, blah, blah, blah. And we'll see each other on the next day of LeetCode 30-day challenge. Bye-bye.